Professor Eric Nielsen from New Mexico State. So you have 15 minutes each. Christoph, can you start?
Yes, thank you very much, Carl, for the introduction. Let me start. Can you see my presentation? Okay, so welcome everybody to this talk on planetary population synthesis, comparing theory and observation. The motivation for planetary population synthesis is clearly an observational one. It is, of course, this enormous increase in observational data on exoplanets since 1995. And here you have a diagram that you have seen already many times. This is, of course, the mass distance diagram. Here we have 51 PeG-B. And since then, there was an enormous increase of knowledge, both from the ground and also from space-based missions. And more is, of course, to come soon. And we will hear about that, more about that later this week. Now, if there is one word characterizing this population of exoplanets, is certainly diversity. And this is not only the mass distance diagram, but also when you look at things like eccentricities, compositions, luminosities, orbital elements, architectures, and so on. And we would like, of course, we would like to use all this data to better understand planet formation and evolution. But actually, this is not so completely trivial. And the reason is maybe twofold. So when we observe a planetary system, what we see is the result of the nonlinearly combined action of all mechanisms that act during planet formation and evolution. And if you have a theoretical model, say on grain opacities in protoplanetary atmospheres, this is not so easy to constrain directly, because other processes are important as well. Not only the grain opacity, but maybe also the solid accretion. And second, for exoplanets, we typically only have limited information on individual exoplanets. But of course, we have now demographical information. And here, this is where population synthesis comes in. So population synthesis is basically a tool. It is a tool to use all known exoplanets to constrain planet formation and evolution models, to test the implication of theoretical concepts. So say you have a new idea what regulates gas accretion, maybe magnetic fields or so, and you would like to know how your models is expressed in a statistical way and how it compares to the population we know. It can also be used on the observational side to predict the yield of future instruments. And generally speaking, it provides a link between theory and observations. It is a statistical approach rather than comparing individual systems, which is, of course, as important as well. The solar system, TRAPPIST, Kepler 11 and such. These are also important. But here, what we do is do statistics. And this means that we need to compute the formation of many planetary systems. And thus, the model, the theoretical model, must be fast and simplified. But of course, it should capture all known key effects as far as we know them nowadays. This is, of course, not the final truth. So what we do here is to develop a global end-to-end formation and evolution model, which builds on detailed theoretical studies of specific physical mechanism, and we then combine it into such an end-to-end model. And what end-to-end in this context means is that when we really start with small objects in a protoplanetary disk, and we want to directly predict a full-fledged planetary system with observable properties. So in this sense, because it builds on all these detailed studies, these models also reflect the general progress of the field, and it means that they also change as a function of time. And there are different choice models nowadays, population synthesis models, and I put here a number of them, both for the core accretion model, but also for gravitational instability. So what is common to all of these models is basically this workflow here. So we start with models of individual processes. We heard about some of them in the previous talks, like evaporation, like the dissolution of solids in the interior, so accretion process, migration, disk evolution, and all of that. And we try to get the essence out of these models here, which is not necessarily trivial, but we try to do that and try to unite them in these global end-to-end formation models. And now, what comes also in are the disk properties, because the disks, the protoplanetary disks, they are, of course, the initial and boundary conditions for planet formation. And what we know from observation is that not all disks have the same properties. So we can try to derive, which is also not trivial, to derive from observations essential properties like the disk gas mass, the dust masses or the dust to gas ratio, and the disk lifetime. And here you have some actual observations with ALMA. And the underlying idea here is that the observed diversity of disks is the reason for the observed diversity of planetary systems. Once we have these two elements, we can start our end-to-end model with different initial conditions, drawing in a Monte Carlo way from this probability distribution, and each time compute one synthetic planetary system. And then we can do that 1,000 times or so, and then we get a synthetic population. In the next step, we want to apply an observation detection bias, because it's clear that with our instruments, we cannot detect all planets. So what we do here is to sort out those synthetic planets which we could have observed with a given technique. So now we get the subpopulation of detectable synthetic planets. And this one we can now compare with the actual observed population. And we can compare a lot of important statistical things like frequencies, occurrence rates, distribution of masses, radii, magnitudes, the architecture, the multiplicity, correlations with stellar properties like metallicity, and all of that. And in most cases, we will see that there are differences, so there won't be a very good match. And so what we have to do, and this is the point, we go back, we try to understand where these differences are coming from, and we improve our model. So we can maybe just change some parameters, we can improve them, and sometimes you also have to reject the model and say, no, this really doesn't work. And like that, we have a feedback loop which can help us to improve our understanding. Sometimes you have also a model which is satisfactory, at least in some aspect. And this is interesting on the observational side, because we can now use it to make predictions what happens when we are building the next generation of instrumentation. So we can say what happens if my direct imaging instrument has an inner working angle which is only half as large as my current instrument. And we can even use that to design instrumentation which yields the most most compelling constraints. And this then goes into the observed population. And then we basically have another feedback loop which helps to improve our understanding. And it's important to see here that one learns a lot, even if a synthetic population does not match the observed one. Good. What is now included in this global models? There are different ones. I'm just talking about one example. This is the generation 3 Bern model. And so the first ingredient is a disk model. And this is actually for two disks. One is for the gas disk, which is here taken to be a viscously accreting disk, including stellar radiation and internal and external photoevaporation. And here we calculate the vertical and the radial structure of the disk. And we also have a disk chemistry model included. Then this is a planetesimal-based model. So we have a disk of planetesimals characterized by a surface density and a dynamic state, and also a composition. And then we put small planetary embryos in it, lunar mass, and we let them grow. And they can grow either by the accretion of planetesimals or of pebbles in another model. And here things like the capture radius and the collision probability come in. The planets can also accrete gas, and for that we solve the internal structure equation of which Ravid Helet was speaking about, and this gives also the radii and the luminosities. And finally, importantly, there are interactions. So on one hand, these concurrently growing planets, they can interact gravitationally through n-body interaction. This leads to scattering, to collisions, to capturing, to mean motion resonances. And you also have the interaction with the gas disk, leading to orbital migration and damping of eccentricities. And finally, during the evolution, when the gas is gone, things like bloating or atmospheric escape, of which we heard before, are then included. These models are nowadays quite rich in microphysics, but they are low dimensional. So there are no 2D or 3D hydrodynamics, because this would take far too long to simulate the entire life of many planetary systems. And there I list here a number of simplification that different models make, and you can have a look at the longer version for more details. So now with that in place, let us have a look at what such a global model can predict. And what we are looking at now is the formation of the mass distance diagram. So we start now at t equals 0. We have the time here, we have mass and distance or period, and we look at the formation around solar mass stars. And we do that for 1,000 systems, 1,000 stars, and each of the systems initially contains 100 embryos which have a lunar mass, about 1% of the Earth's mass. And then we vary in a Monte Carlo way the dust to gas ratio, so how many solids we have, the initial gas mass, and the disk lifetime. And then you're going to see now how all these planets grow. Since we plot all 1,000 systems, you cannot see which planets are together in one system. By the way, the black crosses, this is the solar system, but you can see how it grows and evolves population-wise. So let's get started. So, and exactly, the colors give you the bulk composition of these planets. So this is at the beginning, the planets grow upwards, more or less, because the growth time scale is shorter than the migration time scale. But then this changes and they start to migrate in. We see here the formation of many close-in low-mass planets. We also here have a clump of terrestrial of giant planets. Here we are in the evolution phase. This is tidal removal of planets. And you also have, you saw these horizontal bars, and they show you the eccentricities of these planets. So this is the peri to apoastron distance. And then we can analyze such a population in many, many different ways. I don't really have the time to go into details here, but what we can maybe say is that when we just look in a very quantitative way, is that several fundamental features of the observed population can be recovered, like this close-in low-mass planets, which in the synthetic population are actually an overlay of two distinct populations, which might explain a number of observations. Then we have the cold Jupiters. We have here less planets. We have the distant super Jupiters, ice worlds, and habitable zone planets, which we cannot yet observe at the moment. But the most important message is probably that the variation of the disk initial conditions over a range which is likely occurring in nature leads to a large diversity of planetary systems, similarly as observed. And this was not the case when you go back to formation models maybe 20 years ago. This would not have happened. Now, to finish, or the last two slides, I would now go a step further, because what is an advantage of population synthesis is to allow for a quantitative comparison of theory and observation. And here we're going to do that by comparing with the results of the HARPS survey. This is a radial velocity survey where we observed 822 solar-like stars. And we also have a known detection bias. So we know with what probability we would have discovered planets of a given mass and semi-major axis or period. And this you can hear. So these are the actual observation results. The points are all the planets we detected, and the lines are the detection probabilities. And now we can say, okay, we can just count. We discovered here 161 planets around 102 stars, mean multiplicity of 1.6. And now we can try to see what would have happened if HARPS had observed our synthetic planets. So we take 822 synthetic systems, we zoom in into the period range that we probed, then we apply the Sinai effect, and finally we apply the synthetic detection bias. And now we see what HARPS would have discovered if it had observed our new generation planetary population synthesis. And we can again count, we can make them overlay, and we can count. And we see now that here we would have discovered about 370 planets, around 204 stars, also a multiplicity about 1.6. So in terms, I think you see a certain agreement. There is a cluster here, there's a cluster here. So there's a similar global structure. And the mean multiplicity is also the same. And this is important because it's a proxy for system architecture. But there's, of course, also this factor 2 in absolute numbers. And this could be an effect of initial conditions, for example. And we also see a disagreement here. We don't have hot Jupiters. And that's maybe because we don't include quasi or scattering plus tidal circularization in this model here. So this is an indication that the model cannot capture this physical effect. Quickly, before I'm finishing, another example. This is now a statistical comparison with the Sphere GTO survey. So this is a direct imaging survey, and we will hear more about that by Eric Nielsen for GPIE, but also in general in the next talk. And here, this probes a very different kind of planets and also a different observable, namely the luminosity, which is directly predicted by this model here. And this is the actual detection and the sensitivity we had. So what we found around these 150 stars, and we can then see again, as before, what would we have discovered if we had observed the synthetic planets? And we can look, for example, at the fraction of stars with planets and observed it's about 5.8%, and synthetic is about 3.4. So it's less, but still close given the error bars. So here we see an agreement of the overall frequency. But the distant giant planets in the synthesis are single massive eccentric planets formed from scattering events, because core accretion cannot produce planets very far out. So what we cannot reproduce here is an HR 8799 system, like 4 distant massive giants on rather circular orbits. So we see that these points that maybe there are structured disks which allow planet formation further out, or maybe formation by gravitational instability. And I think I'm already at 16 minutes, Carl, so I will stop now. Thank you very much for your attention. Thank you.
Okay, thank you, Christoph. I think you can all see, how ambitious this kind of research is, and Christoph had only a very short time to describe how they approach this. So I really encourage you to look at his long presentation for a lot more details on how they do this. And so we've got a couple questions that have arrived already, so please keep sending them in. We'll start answering the questions after we've heard from Eric here. So Eric Nielsen, tell us about theory and observations on demographics.
All right. Well, thank you, Carl. Thank you very much to Christoph for that great introduction to what I'll be talking about today, which is exoplanet demographics, and particularly how we use observations to try to guide what we know about theory. I'll be talking largely about direct imaging in this talk, so I always like to start with this great movie of the 4 HR 799 planets orbiting the star from Jason Wang, Christian Marois, a nice sort of illustration of sort of the power of direct imaging, really good at getting these sort of wider separation giant planets. And in particular, demographics is about looking at planets at a population level, take all the planets we know and try to get a sense of, as Christoph says, what mechanisms could have left the planets that we see at the locations where we see them. And again, a focus here in this talk on direct imaging, and so this population of wide separation giant planets that we see with direct imaging techniques. So let me start by just defining terms. What do we mean by exoplanet demographics? I usually think about it as 2 related questions. One, what's the occurrence rate of planets, by which I mean, how many planets per star, and how that occurrence rate changes with properties of the system, whether that's properties of the planet or properties of the star. Are there more high mass planets or low mass planets? Are there more close-in planets or wide separation planets? So with demographics, we can directly test these models of planet formation as well as evolution, models of migration as well. And also predictions for future instrumentation and surveys. How do you build your future telescopes? How do you build your future instruments? Where are the planets going to be that you're going to go and try and study? A little bit more definitions here. 2 similar but distinct terms with a subtle difference: planet fraction versus planet occurrence. So planet fraction is just the fraction of stars with planets. It's a number between 0 and 1. Planet occurrence is the number of planets per star, which in principle can be larger than 1. And so if you imagine a hypothetical where every star in the universe had 8 planets, the planet fraction in that case is 100%. The planet occurrence rate is 800%. And both are usually given over a specific set of parameters, usually based on the survey we use to get these numbers. And so in the direct imaging case, usually you see numbers like 1 to 13 Jupiter masses, 10 to 100 AU, orbiting stars between about 1.5, 2.5 solar masses, the planned occurrence rate for that subset. And in terms of calculation, these are relatively straightforward fractions. For planet fraction, you would just count the number of stars with planets in your sample, count the total number of stars in your sample, divide the two, and that's your planet fraction. Planet occurrence, you would count the total number of planets, divide by the total number of stars, and that's your planet occurrence. And so it seems straightforward, but of course, life is never quite that simple. And the thing you have to remember is completeness, that depending on your observation technique, some planets are easier to see than others. And you really need to take into account that bias for your particular technique, for your particular observations, before you start making conclusions about the overall occurrence rate. Okay, I'm just going to do a very quick advertisement here before moving on. If you work on exoplanet demographics, we would love to have you as part of NASA SIG2. This is a science interest group that does exoplanet demographics. We meet about once. We have telecons about once a month. So consider joining SIG2 if your work takes you towards exoplanet demographics. And again, this is a short talk. There's a longer talk on YouTube, but if you really want to dive into exoplanet demographics, there's this wonderful archive of papers on the NASA Exoplanet Archive, occurrence rate papers from a number of different techniques. So I highly recommend doing further reading there. Okay. So again, we want to talk about what the observations can tell us about the theory. And so in particular, I'm going to zero in on giant planet formation. As you've heard, there are sort of two paradigms for how giant planets come to be. One is this bottom-up process of core accretion that we heard about today, build up several Earth mass core of solids, which then has enough gravity to accrete gas from the disk. Alternatively, there's this much faster top-down process of gravitational instability, where instabilities very rapidly grow in the disk to planet masses or even brown dwarf masses. Okay, and then let me dive into direct imaging. You're going to hear a lot more about direct imaging tomorrow, but the short version of direct imaging is that it's really a lot like staring directly into the beam of a lighthouse and trying to spot a firefly sitting at the edge of the lamp. This is the sort of contrast ratio that we have to deal with: a very, very faint object next to a very, very bright object, the host star. And we can make our lives easier by going after young planets. This is why we're talking about direct imaging so much at this conference dedicated towards young planets, that young planets are still hot and bright from their initial formation. And so it's much easier to see a young planet than an older one. And so Jupiter, when it was just tens of millions of years old, was only about 1 million times fainter than our sun in the infrared, compared to in the visible today, where it's about 1 billion times fainter than our sun. So the contrast ratio, the difference in brightness between planet and star, much more favorable at young ages, much more favorable in the infrared. And so another important point, we don't measure mass directly with direct imaging. Instead, we have to turn to our favorite theoretical models to convert the luminosity of the planet and the age of the planet, which we get from the age of the star, into a mass. And so depending on the luminosity we observe at different ages, that can be a very low mass, 1 Jupiter mass planet, could be a very high mass 13 Jupiter mass planet, could be a 73 Jupiter mass brown dwarf. It depends on both the age and the luminosity of the planet. Okay. And again, you're going to hear a lot more about how direct imaging is done tomorrow. But the main ingredient from a direct imaging observation that goes into a occurrence rate calculation is the contrast curve. The contrast curve characterizes how sensitive we were to faint companions as a function of separation from the star. And so usually given separation in arc seconds versus contrast, where contrast is either the flux ratio or the magnitude difference between star and planet. So in observational units, this is separation in arc seconds, and then say delta H magnitude on the y-axis. To convert these into physical units, to convert the y-axis to physical units to mass of the planet, something that we're all very much interested in, we need to use our favorite evolutionary models. We need to use the absolute magnitude of the star, as well as the star's age, in order to convert that delta H into a mass of the planet. And so these are the answers I get for a G0 star that's 100 million years old. And then we use the star's distance to convert the x-axis, separation in arc seconds, separation in AU. Okay, but it's important to remember separation and semi-major axis are two different things. I think this is most well illustrated by this movie of the Beta Pictoris B planet orbiting the star. And so the semi-major axis of this planet is 9 AU, but the separation changes dramatically depending on when we happen to go observe this star. And so your completeness depends on the orbital properties of the planet, but also when you actually make your observations. So orbital phase is very important as well. Okay, and then I'll skip over a lot of steps that you can check the YouTube talk on for more details, but this leads to a plot that I could call the tongue plot, or the depth of search. And this is basically a summary of how complete a given direct imaging survey was, in this case to giant planets and brown dwarfs, as a function of mass and semi-major axis. And the contours give the number of stars to which we could have seen an object of those given parameters. And as an example, if you take this 160 star contour, it covers brown dwarf masses from about 10 to 80 AU. There's about 3 brown dwarfs that we detected with this survey in those contours, and you can just read the occurrence rate right off the plot. 3 out of 160 is the occurrence rate of brown dwarfs from about 10 to 80 AU. It gets more tricky as you get to the tip of the tongue, but I'll leave that to the YouTube video for a little bit more in-depth discussion of what you do in those cases. Okay, and in the final few minutes, I'm going to talk about some of the recent results from on Exoplanet Demographics, again from direct imaging surveys looking at wide separation giant planets. I'll start with the group that I've been part of, the Gemini Planet Imager Exoplanet Survey. Definitely want to make sure I highlight the really impressive work by the entire team. Nothing that I'm talking about today would be possible without the contributions of everyone who's been part of GPIE from the beginning. Okay, so 3 big demographic results from the Gemini Planet Imager Exoplanet Survey. Number 1, when we divide the tongue plot up by mass of the host star, so we put low mass stars on the left, high mass stars on the right, and then we zero in on wide separation giant planets, we see that all the wide separation giant planets detected by the survey orbit high mass stars. So that's 6 separate planets orbiting 4 separate stars, all higher mass stars. And so at better than 3 sigma confidence, we can say that the planet fraction is higher for higher mass stars than it is for lower mass stars. Okay, number 2, planets versus brown dwarfs. So if we just divide the plot up by mass here, so use the canonical 13 Jupiter mass deuterium burning limit as the boundary between planets and brown dwarfs, fit a parameterized model to both sets of populations, we find at somewhat weaker confidence, between about 1 and 2 sigma, evidence that we're looking at 2 separate populations. We're not looking at the same population for wide separation giant planets as wide separation brown dwarfs. Rather, they're 2 distinct populations, again, at sort of the 1 to 2 sigma level. So again, evidence that we're not looking at the same underlying distribution for planets and brown dwarfs. Brown dwarfs are not just the high mass end of the giant planet distribution. Okay, and third point, if you look at the occurrence rate of planets as a function of semi-major axis, we have an answer for the inner part of the solar system from radial velocity work, for example, Andrew Cummings' paper in 2008, and we see this rising occurrence rate as a function of semi-major axis. As you move away from the star, you have more a large number of planets per star. And now with GPIES, we have the answer at the far end, that between about 10 and 100 AU, we see this declining occurrence rate as you move further away from the star. And you put those together and you get a peak somewhere around the snow line, somewhere around a few AU. And this is very consistent with results from radial velocity surveys, a recent paper by Rachel Fernandez, paper from BJ Fulton earlier this year, all pointing to this, this peak in the distribution of giant planets, somewhere around the snow line. Okay. So again, not the same power law for the inner and outer solar system. All right, so what does this all mean for planet formation theory? Again, I talked about these 2 paradigms, core accretion versus gravitational instability. And if you look at the predictions that each of these make for what sort of wide separation giant planets you would see with an instrument like GPIES, the core accretion predictions are most well line up with the wide separation giant planets seen with GPIES. The gravitational instability predictions, not so much for the giant planets. However, the wide separation brown dwarfs we see with GPIES while core accretion doesn't look like a good explanation for how those came about, gravitational instability remains a plausible mechanism for forming those brown dwarfs. And again, so some of these are at weaker confidence. Some of these observations are at weaker confidence than others, sort of 1 to 2 sigma. So definitely more work is would definitely be helpful here. Okay, and I want to mention as well that since our work came out, there's this wonderful paper by Arthur Vigan looking at another planet survey with using a instrument at the VLT called SPHERE. The SHINE survey recently published demographics on the first 150 stars they observed. Here's what their tongue plot looks like and their detections. So first of all, a very nice agreement between our two surveys. We both see this trend where higher stellar mass corresponds to a larger planet fraction. They use a different technique, as Christoph mentioned. They looked at population synthesis tools to try to fit their observations. And when they try to fit planets and brown dwarfs around solar type stars, they find that the core accretion population synthesis by itself can't reproduce the results. The gravitational instability population by itself can't reproduce the results. Instead, they need a mixture of those two mechanisms. And in particular, it nicely echoes the GPIES results that you can possibly explain the planets with core accretion and the wide separation brown dwarfs with gravitational instability. But again, more work, more objects would certainly be helpful here. Okay, so I'll wrap up by putting up my conclusions here. So again, demographics are a very powerful technique that allows us to directly test predictions from theories of both planet formation and again evolution. That the planets probably don't stay where they're born. Models of migration are also testable using demographics. My personal feeling here is that most of the demographic results from direct imaging so far are pointing more towards core accretion than they are towards gravitational instability. But again, this is somewhat limited statistical significance, and it'll be nice to have more observations. I leave you to go check out the YouTube version of this talk where I discuss some future instrumentation and future possibilities for improvements in demographics. But you'll also hear that as well on Friday when you'll hear about future telescopes, future instrumentation. And I'll put up my advertisement one more time and I'll stop there, and I'm happy to take any questions.
Okay, thanks very much, Eric. I mean, there's a tremendous amount of observational work by your team and the Vigan team to get those results and make them available for comparison with the kind of models we've been seeing today. All right, so I want to encourage people to go into the Q&A tool and upvote some questions. If you're might be a little thrown off because we still have questions from the earlier session this morning in the list, but look for the timestamp on the question. If it's after 10:30 Pacific time, then it's relevant to the two talks we just heard. Maybe the time zone of your local area is shown instead of Pacific time. I couldn't say. But looking at the upvotes that we have so far, there's a couple questions about hot Jupiters, Christoph, in your models. Why you don't produce them. You mentioned a possibility for that earlier. Is there any thing you would do to just drop one into your simulation to see what happens to the rest of the system?
Yeah, it's actually quite an interesting subject. So we noted that this population synthesis does not reproduce the observed hot Jupiter population, although there are not many, but still. And this is despite including full disk-driven gas-driven migration. But what we did see is that in the model, there are giant planets colliding with the host star. And in the model, we do neglect that instead of colliding these giant planets, they are scattered by other planets onto very eccentric orbits. They could be tightly circularized and then lead to the formation via this high eccentricity migration and tidal circularization. And we then looked at what are the properties of these objects, although we do not include this tidal circularization, but we can still look. And we saw that they are probably responsible for forming the dominant part of the hot Jupiters. And this is in line with the observation that many of these hot Jupiters actually have very high obliquities, and they are not in the plane of the disk. And this is in contrast, although it's not so simple, but probably it's in contrast with the predictions of disk-driven migration. So this was an indication that there's probably indeed another formation channel that is not included in the current model. What was interesting is that when we then looked, we have some, but not enough, which are coming there by disk migration compared to those which end up there by scattering. They are very similar in terms of host metallicity. The only thing which differs is the remaining architecture of the other planets in this system. When you have disk migration, you can have, like it's also observed, maybe a low mass, another low mass planet, maybe in mean motion resonance to the hot Jupiter. It's very rare, but it does exist. While in the high eccentricity case, there is another giant planet far away, eccentric, massive, but nothing else. And this is the only thing which really differs in these two cases.
Okay, thank you. I guess another question for Christoph that has been voted up is how well do your models, predict solar system-like architectures? How often does that happen?
Yes, this is. I saw that this question already in the previous session, and the model does produce basically four classes of architectures. Can't go into all details, but one class is indeed systems which are similar with the solar system in a very broad sense, in the sense that there are closer in low mass planets, one or two giants, and then again outer ice giants. And if I remember correctly, I think this architecture is something on a 10% level of all synthetic systems. What the model at the moment does not reproduce is that the giant planets are in the solar system at 5 and 10 AU. Rather, in the model, they typically end up at something like 2 and maybe 4 AU. And the reason for that is that in the solar system, probably we don't know, but it's at least possible that there was the grand tack. So there was this special situation where, unlike in normal situation, the two giant planets migrated outwards. And this is something which is not included in this kind of migration models. But yes, so this is another physics that it tells you that in order to reproduce the solar system, you probably do need these mechanisms. While on the other hand, the pileup of extrasolar giant planets at about 1 AU is pretty well recovered in these models.
Okay, very good. So I'll take a question here that's intended for Eric. Just someone's asking about direct imaging data reduction techniques, the impact of those on your population results. So how are they taken into account?
Yeah, so it's a very good question. I sort of skipped over it in the live version of the talk, but the contrast curves that we make are incredibly dependent on what data reduction technique we use. And in particular, one thing that we found over the last several years of doing direct imaging is you can improve your contrast ratio, you can improve your sensitivity by doing a more careful data reduction technique. New data reduction techniques, specifically ways of subtracting off the PSF of the star, have let us essentially dig deeper than we could without those techniques. And so yes, the contrast curve absolutely reflects whatever data reduction you did to dig out the planets. The best contrast curves usually reflect injection recovery techniques as well, that you put simulated planets into essentially your raw data, and you see if you can dig them out at the end. And that really tells you that if you've done anything in your data reduction process that might have, say, reduced the flux of your planet. And so, yeah, the contrast curve informs all future occurrence rate calculations, and it hopefully covers everything you've done to your data, from the observation to the reduction to all other steps.
Yeah, and so your tongue plots that you showed include all of these considerations.
Yeah, absolutely.
Right. Okay. Well, I see another one that's been voted up here for Christoph. They're asking about the initial conditions for the population synthesis models. I mean, how are you varying the properties of the star when you go ahead and do this? Do you have only one type of star, or do you have something else, a distribution of star types, metallicity, binarity, etc.?
Yep. So the simulations I showed you, they were all made for solar-like stars, but the metallicity was varied assuming that the disk metallicity, so the dust to gas ratio in the disk, is the same as in the star. And when you do this assumption, you can derive it from measuring the metallicity distribution of solar-like stars. And this is an initial condition. This dust to gas ratio is very important because together with the gas mass, it sets the amount of solids that you have. And we heard that already in the talk of Andre, that the amount of solids you have is really the crucial initial condition, although also external photoevaporation is also important and therefore cluster environment. This is one part of the answer. The other one is regarding stellar mass. Here it's not varied, here it was fixed, but we did of course also population synthesis, especially for low mass stars, but also for more massive stars. Low mass stars, very interesting in terms of transit surveys, TRAPPIST-1, and also radial velocities, Carmenes and all of that. More massive, especially interesting in terms of direct imaging. And you see then clear trends of what kind of planetary system architectures and types are becoming dominant as you change the mass. And this is a very important we need to check, to constrain these models.
So maybe a reason that you went for the one solar mass typical example you showed us is because that was what the Kepler mission targeted for its demographic study? Yeah.
Absolutely. I mean, Kepler, besides maybe HARPS and now also all the new surveys like the California surveys and the GPIES are of course, they have many or more, the direct imaging has also more massive stars, but the other ones are really centered on solar-like stars.
All right, well, we still have plenty of questions, so I'll keep going through the list here. This is another algorithm question, but this time it's for Christoph, which is that, is there something that machine learning could do to help you in your population synthesis work?
Yes, this is a very good question, because I talked about this problem that when you include a lot of physics, these models, despite being low dimensional, they are already computationally intense. So for example, this simulation with 1,000 systems, this was about 1 million CPU hours. And this compromises a little bit one part of the population synthesis, namely to vary the parameters and the underlying assumptions of the formation model. When it takes so long, you can do maybe 2 or 3 or 4 simulations, but of course you would like to do many more. And one way out is to train a machine to predict the outcome given some initial conditions and given your model. This works pretty well when you have one embryo per disk. Then this model is completely deterministic and you can train the machine quite well. However, when you have the N-body, there's still a trend, right? Metal-rich disks still give more probability giant planets. But we saw, for example, that I talked about these different classes, and one we distinguish are this like solar system classes architecture with both low mass and high mass giant planets. Another class are systems with only giant planets, which underwent dynamical instabilities. And if you compare the initial conditions, they overlap over a large part. So there it seems to really matter how exactly the timing of the growth of the two giants were, whether it's got a system which still remained kind of stable or where the eccentricity became large and there was scattering and everything was destroyed. So although the model is still deterministic, in terms of the initial conditions, it's a little bit chaotic. And there, it might be more difficult. But we have a paper, actually, it's interesting that you asked that, by a colleague of mine, Martin Schlecker et al., 2021, which exactly looked at machine learning in this context.
Okay, thanks for that. So we still have, some of the questions are getting answered. Thank you to those of you who are doing that. So we still have another question for Christoph about the role of gravitational instability in your models along with the planetesimal embryos coming together. Do you include that, and how would it change things?
Yeah, this is so I think in a more, no, this is not included. At the moment, this model is in the sense a little bit, you know, this development cycles of these global models, they lag a little bit behind the latest development in the field. And here we started at a relatively late stage, planetesimals and embryos. But of course, you would like to go back in time. You would like to start, in the best case, during the infall, look what the solids did, because they start moving, drifting and growing very early probably, and you have observational indication of very early growth process. But this is at the moment not done, and I think this is certainly a goal, but it's not included in this generation here.
Right. Well, it seems like the planets at wide separations are the real challenge still. Things that are not the brown dwarfs that Eric has been finding around solar type stars. Are you able to even are we able to make large planets around solar type stars in any context? We've seen some debris disks that have evidence for planets near 100 AU, and we find that very perplexing.
So the model does produce distant giant planets on eccentric orbits,
Okay.
which are the results of scattering. And the scattering can either happen at late times, but it can also occur relatively early, in the sense when the gas disk is still there. What can happen then is that a Neptune mass planet gets scattered on a far out orbit, gets circularized there, and this one can then undergo gas runaway accretion out there. And this can then lead to the formation of a giant planet at large distances. But this is a little bit a specific channel. It would not produce a single planet. Typically there are two because of the scattering, and it will also not produce something which looks like HR 8799, which are the orbits don't seem to have we don't know, but it doesn't look like the system underwent very violent dynamic interaction. And this is something we could not produce in this channel here.
Okay, thank you very much. We'll have to hold it at where we are now, because we're already taking time away from the next speakers. So thank you both for discussing this very important topic, and we look forward to some